To machine a single precision part by hand, an operator must measure the dimensions and manually score the metal. Next, they must align the drill bit perfectly to that specific mark, and finally make the cut. It is a slow, methodical process. Attempting to scale that exact manual process for 1,000 parts introduces a severe bottleneck. Every individual measurement creates an opportunity for compounding unpredictable human error, and the idle time spent positioning each unit destroys production efficiency. The engineering solution to this bottleneck is the implementation of dedicated production tooling, specifically jigs and fixtures. Both of these devices are designed to accomplish the same ultimate function, eliminating the need for individual workpiece marking and manual positioning prior to every cut. By shifting the burden of precision from the operator's hands to a rigid physical tool, a machine shop can achieve high-volume, repeatable manufacturing. On the shop floor, the terms jig and fixture are frequently used interchangeably. Because they are both heavy chunks of metal used to secure workpieces, they appear to perform the exact same job. This image shows a standard drill jig. Notice the silver metal plate with guiding holes mounted directly over the dark workpiece. Now contrast that with this mechanical fixture. It features a heavy black vise with spring tensions and ball-end handles to clamp the material. Despite their visual similarities, these two devices serve entirely distinct mechanical purposes. That distinction is dictated entirely by the relationship between the tool holder and the cutting tool itself. To understand why they look and operate differently, we have to deconstruct the physics of active tool guidance versus rigid positional support. A jig is a production device that holds and supports the work, but its defining characteristic is that it actively guides the cutting tool into the workpiece. This diagram illustrates the critical component making a jig function, the hardened steel drill bushing. As the drill descends, it passes through this bushing. The steel sleeve physically restricts the bit, dictating its exact trajectory and ensuring it strikes the material at the predetermined location. Because the tool path is physically locked in place by the bushing, the operator simply pulls the lever. Drastically less technical skill is required to execute a perfect cut. The physics of drilling or reaming explain the jig's design. The forces generated here are primarily axial, meaning the energy pushes straight down, vertically, through the tool and into the machine bed. Because there is very little lateral stress trying to push the workpiece sideways, jigs can be built with much lighter materials. In some low-torque applications, they don't even need to be clamped down and are simply held by hand. A jig's architectural priority is precise trajectory control. A fixture, by contrast, is a device that securely holds, locates, and supports the workpiece, but explicitly does not guide the cutter. Fixtures are mandated for heavier manufacturing operations like milling, shaping, planing, and turning. Unlike a drill press, heavy milling operations generate highly dynamic, multi-directional cutting forces. The cutter impacts the metal from the side, creating severe vibrations and explosive lateral stress. To counter these violent forces, fixtures demand robust construction. This requires heavy steel base plates, pneumatic lines, and toggle clamps to lock the component. To successfully resist that intense lateral force without shifting, a fixture must be firmly bolted directly to the heavy table of the machine tool. Because fixtures do not feature guiding bushings, the operator faces a different alignment problem, ensuring the unguided cutter hits the exact right coordinates on the metal. This line drawing shows the external calibration required. Operators must align the milling cutter against reference edges using separate accessories like set blocks and feeler gauges. This process cannot be bypassed, meaning operating a fixture requires a higher baseline of technical skill. A fixture trades active tool guidance for absolute positional rigidity under extreme multidirectional stress. Let's apply these rules to practical engineering schematics to accurately classify two different tool bodies. Look at this second, nearly identical schematic. Focus on the exact same upper portion of the U-shaped tool body. The guiding holes and bushings are entirely absent. The boring bar passes through open air. The device is merely holding and supporting down below. Lacking tool guidance, the second device is classified strictly as a boring fixture. It is the specific mechanical function, not the general U-shape or profile of the metal block, that dictates exactly what the tool is. Despite this functional divide, both jigs and fixtures share several mandatory design requirements to do their jobs effectively. The first shared requirement is locating. This establishes exact positioning by registering reference planes on the component against pins in the tool. The second requirement is clamping, which provides the necessary grip to maintain that perfect position once cutting force is hit. Good tooling must also adhere to the principle of foolproofing. The tool is physically shaped so that it is impossible for an operator to insert the workpiece backward or upside down. Structurally, designers must include adequate relief areas within the tool body to provide chip clearance. If metal shavings cannot escape, they will pack down and jam the operation. Finally, both tools must be constructed from highly durable materials, usually high-carbon steel or specific alloys like phosphor bronze. Utilizing these tough, wear-resistant metals is non-negotiable. The tool must hold its precise internal geometry perfectly, even after thousands of heavy machining cycles. Whether the job requires guiding a delicate drill bit or resisting a violent milling cutter, success relies entirely on flawless, repeatable workpiece positioning. This graphic places both devices side by side. The drill jig, on the top left, dictates the tool path. The mechanical fixture, on the bottom right, dictates workpiece stability against mass and force. This comparison table highlights the practical results of those functions. Jigs are lighter in weight and easier to operate. Fixtures must be heavier, robust, securely clamped to the work table, and demand higher operational skill. In production tooling, mass follows force, and structural complexity follows guidance. On the modern shop floor, flexible manufacturing systems and CNC machining have updated how we use these tools. A CNC machine relies on internal computer programming to physically guide its own cutting tools to the correct coordinates. As a result, the industrial need for complex, tool-guiding drill jigs has decreased. However, the massive physical forces generated during machining remain exactly the same. The fundamental principles of heavy, rigid fixturing are absolutely critical to making modern automated machinery work. Utilizing properly engineered work-holding devices yields distinct, measurable advantages. By locking in dimensions physically, manufacturers drastically decrease cost, improve the precise quality of the final product, and push productivity per hour to its absolute maximum limit. Engineering exact repeatability into the physical tooling is what transforms a singular machining act into a reliable, scalable global industry.